Okay, so today topic is equipotential surfaces. We all know very well about electric field. Electric field is visualized with the help of electric field lines. Similarly, the potential at various points can be represented graphically by equipotential surfaces. Adjacent points that have the same electric potential form an equipotential surface. On an equipotential surface, the electric potential V is the same at every point. When a test charge moves on an equipotential surface from point to point, the electric potential energy remains constant. It means potential energy is not changing during the motion of charge on the equipotential surface. It also means that no work is done on a charged particle by an electric field when the particle moves between 2 points on the same equipotential surface. So electric field E is perpendicular to displacement of charge moving on the surface. Now field lines and equipotential surfaces are mutually perpendicular. In general, field lines are curved and equipotential surfaces are curved surfaces except uniform field. Let's see different arrangement of equipotential surfaces. Here the field lines of charges are represented by red color, and the intersection of equipotential surfaces with this plane, the cross section of the surface, is shown by blue color. Field lines and equipotential surfaces are perpendicular at every crossing. Here, 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 here. This is the simple case of a single positive charge. Mostly the adjacent equipotential surfaces are drawn at same potential difference. In the region where the magnitude of E is large, for example here, the magnitude of electric field is high. As you move away from the charge, the magnitude of the electric field is getting less and less. So in this region, the equipotential surfaces are close together because the field does a relatively large amount of work at a relatively small displacement. For example, like this one, near the point, the electric field does large work on test charge. If I place a test charge here, then electric field does greater work on the test charge. On the other hand, where the electric fields are weaker, the equipotential surfaces are far apart. For example, here they are. If I draw one more equipotential surface, then that will be like this. So at large radii, the electric fields is weak and your equipotential surface is far apart. Okay, now you can also see this in the case of an electric dipole. Here you can see that to the left side of the negative charge, the equipotential surface is at larger distance. Similarly, on the right side of the positive charge, the equipotential surfaces are at greater distance. At equipotential surface, the potential V has the same value at every point, but it is not necessary that electric field also has same value at all points. Now again, let's look at the figure B. Here we can see equipotential surfaces of different volts, of different potential. The one which is near the charge has higher potential. As we move away from the charge, the value of the potential is getting less and less. If we look at the equipotential surface of 30 volts, this one, the magnitude of E is less here on the left side of the negative charge, this one, as compared to its magnitude in between the charges here. Also, if you look into the figure C, where equipotential surfaces have been drawn between two positive charges, here electric field E is 0 in the middle, but at any other point on this surface, let's suppose this surface, it has electric field which is non-zero. From symmetry, the equipotential surface produces by a charged particle or a spherically symmetrical charge distribution are a family of concentric sphere. For a uniform electric field, the surfaces are family of planes perpendicular to the field lines. So let's suppose here I have a positively charged metal plate, and this side I have negatively charged metal plate. The field lines will move from positive towards the negative charge because it's a uniform field, so electric field lines are straight, and the equipotential surfaces are perpendicular, or equipotential planes are perpendicular to the field lines. So let's do some numerical, which is somewhat somehow related to the equipotential surfaces and about the summation of the charges.